All right, Unit 7 review. So this is our first section that we looked at. I put these in the order of the book. So like 5-8, I wrote this stuff first, even though it wasn't the order that we did it, in real time. So 5-8 was our exponential growth and decay problem. So the including applies to these bullet points down here. So I'm gonna write down just the exponential growth and decay. So you guys can jump right into this formula right here. In the notes, we did the whole separate, integrate, solve for y, and that's how we figured out what this formula is. You don't have to recreate that. You can just write this formula down, start plugging things in. So let me show you guys a couple of things. So C right here is always the initial condition that they give you. So that's like you sub in 0 for t, that's the value that you're gonna get. T obviously is time. K is some sort of constant. It's either a growth or a decay constant. It'll have a positive value if it's a growth constant. It'll have a negative value if it's a decay constant. And you want to make sure when you guys find this that you write down every decimal that you possibly can, because we saw a couple examples of how inaccurate your answer can be if you round that value of K to only 2 or 3 decimal places. And then Y is just the value of whatever the population is. You might be doing an actual human population. It might be bacteria that's growing. It might be carbon that's decaying, something like that. Population, whatever it is. Okay, so like I said, launch right into that. You guys are always gonna have 2 initial conditions that you can find. Your first initial condition will allow you to solve for C. Your second initial condition will allow you to solve for K, because at that point you'll have the value of C as well. So 2 different types. Finding a time when the population has reached a certain value. So finding a time means solving for T. And then when the population has reached a certain value. So reaching a certain value means that you are given a value of Y. So you'll be given a value of Y and then you'll be asked to solve for T. These are the ones that are slightly more challenging, because if T is the one that you're missing, that's stuck up in a variable. You're gonna have to divide, you're gonna have to take the log of both sides, and you're gonna have to divide by K again. So these are the harder of the 2. You're gonna have one of these on the test. Okay, there will be one of these where you're given a population value and then asked to solve for the time. Like it'll be at what point did the population reach this? And then you're gonna have to solve for T. So you guys will see one of those on your test on Monday. And then the reverse is finding a population value, meaning solving for Y at a given time. So you'll be given a value for T and then you'll have to solve for Y. These ones are the easier of the 2, because that just means you plug in a value of T and Y is already by itself and you just get the value of Y. So you'll see one of those. So 2 of these type.
Given K?
You're not given K, but you have those initial conditions that allow you to solve for K.
Okay.
So the 2 initial conditions allow you to solve for C and solve for K. So at that point, you've already built your equation. You have a value of C plugged in, you have a value of K plugged in. This gives you a value of T to plug in, and then all you have to do is just plug it into your calculator and solve for Y.
So on top of those, we find K and C and then
Correct.
solve for T given Y.
Correct, and that part happens first. Solving for C and for K happens first. All right, so next, finding a general solution to a separable differential equation. So we had a 3-step process at this point. So step number 1 was we separate the variables. Typically it's a dy by dx, which means the dy stuff is always on the left, the dx stuff is always on the right, so we have to separate the variables onto opposite sides of the equation for this to work. Step number 2 is we integrate both sides of the equation. Any integration methods that we've done so far this year are fair game. So the last chapter did all of our integration methods. So it could be just a basic antiderivative, the antiderivative of sine, but it also might be something where you have to do a u substitution, perhaps an inverse trig, anything that we've done so far is fair game. Okay. Step 3 would be to solve for y, to get the y by itself. And remember the notes we wrote isolate so that it's just like an easy separate, integrate, isolate to help you remember that step-by-step process. And then later in those notes, we figured out how to find a particular solution. This is the one that happens more often on the AP test. You guys saw those sample AP problems the other day. You still do this same process, and then at some point you have to solve for C. So steps 1 and step 2 are always the same. You can either do solving for C as step 3 and then get y by itself, or you can get y by itself first and then solve for C. It doesn't matter. So this just means, like, let's say as step 3 or step 4, solve for C using the initial condition. So we could just tack this onto the end as a step 4, or you kind of just insert it right here as a step 3, and this becomes step 4. I think we've seen enough examples. We've talked enough about, like, oh, sometimes it makes more sense to just get C right away if they give you a 0 for X, let's say, and C ends up by itself. Yeah.
For the finding the population value at time, is there one problem with that also?
Yes, one of each of these. Yeah, one of these and one of these. And then with these, I know there are 3 total of these. There are at least one of each. I'm trying to remember which one. I think it's the particular solutions that I put 2. So I think it's 1 of these and 2 of these, but I will double check before you guys leave. I know there are 3 of these total. Okay, Newton's law of cooling. That was the murder mystery day that we did. So this is a very, very similar equation to this, except this time we've got y equals CE to the KT, and then remember we end up with this plus S on the right-hand side. So I will label and identify all of those pieces here too. All right, so this, y is the temperature of the object. So we saw some that, is a glass of water was the object. We saw a couple where the dead body was the object. A little bit more exciting than a glass of water. So temperature of the object is this one right here. The S, remember, is the temperature of the surroundings. So the freezer that the water was going into, that temperature, or the room in which the body was found, that temperature. That's always going to be a part of your formula. And then these K and T, same as we had up above, growth constant, decay constant. If the object is warming up to meet the temperature of the surroundings, K would be positive. If the temperature is cooling down to meet the temperature of the surroundings, K would be negative. T is still time, and then C is not the initial condition. Remember, it's the initial difference between the two. So the initial difference in the temperature. The water one, for instance, there was one problem that we did that the water was 70 degrees and the freezer was 10 degrees. So the initial difference would be 60. And that's what we ended up using for our value of C. So same general idea with these. You will have 2 ordered pairs that you'll be able to plug in. And you should be able to either solve for T or solve for Y, just like the other one. I gave you 1 of each of those. Okay, so 2 of these problems, 1 where in the end you're solving for Y, 1 where in the end you're solving for T. So same idea as these. Real quick summary, because people always ask how they're supposed to tell the difference between these 2 problems, because it's not going to say use Newton's law of cooling or like use a general exponential growth or decay. Newton's law of cooling is always talking about temperature. Okay, if they're talking about the temperature of anything, it's Newton's law of cooling. The general growth and exponential growth and decay problems are talking about some sort of population and how that population is growing or shrinking. These never talk about temperature. These are always exclusively talking about temperature. So that's how you know the difference between the 2 of them. These ones also mention some sort of surroundings. It's in a room, it's in a freezer. There's another like 3rd temperature that's mentioned. So that's how you know those are Newton's law of cooling. Okay, so any questions on that topic? Okay, so the last thing, this is actually one of the first things we looked at, but just numerically in the book. 9.3 is our last section. So sketching a slope field on an interval given a differential equation. So just some tips there. I always like to find the slopes of 0 first. Like we could see those patterns. There was one where we said every time y is 2, there's a slope of 0. So we just sketch in those slopes of zeros, and we figured that every time x was 0, the slopes were 0. So I always like to find slopes of 0 first. And then after that, it's just kind of a plug and chug. You're taking the remaining ordered pairs and you're plugging them into that differential equation. So you plug all of the xy ordered pairs into the differential equation. And that tells you the slope, so then you just sketch in this teeny tiny little slope, just a little line segment that has the slope that you're supposed to have. All right, and the rest of the slope field stuff is on the back. Any questions on just sketching them? Matching slope fields. So you guys will have a matching section. I forgot to give you details. This one, you guys will have one slope field that you have to create yourself. And then you'll have one section of matching. There are 4 differential equations and 4 completed slope fields. And you guys will have to match, you know, like 1 through 4 with A through D, which differential equation goes with which slope fields. So I would say definitely look for slopes of 0. Also look for where the slopes are undefined. Those are usually pretty good ones. And then you can just look for patterns of like when the slopes are positive, when the slopes are negative. Like you guys might notice in one of the slope fields, like, oh, when I'm in the second quadrant, all of the slopes are positive. And then you can see if there's an equation that would make sense for that. Like, oh, it would make sense that this equation would give only positive slopes in the second quadrant, and figuring different things out like that. So 0, slopes of 0 would be horizontal. Slopes that are undefined would be vertical, or at least like moving in that direction, they would be undefined. So just different patterns. And we saw like 2 or 3 of those just yesterday. So hopefully you guys remember some of the tips that we talked about there. And then sketching a particular solution on a slope field, there's not really a ton to say about that. This is a fairly subjective thing. You guys just use the slope field as like a little guide. Like, oh, it looks like it's headed this way, and you just sketch in what you think a general curve should look like. So you guys will have one of those as well. Okay, so any questions on any of these topics that I mentioned here? What's expected of you? Anything? I believe that was 9. Let me see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, so kind of each of these sections has one. Newton's law of cooling has 2. This one also has 2, but I just like separated out which one is which. So same 2 with Newton's law of cooling. One where I give you y and you solve for t, and then vice versa. All right, guys. Any other questions? Yeah.
So when we give like y as a solution, we put it as like the equation of like the actual like number.
You're saying like your answer wouldn't be c equals 4? You're saying like it should be, yeah, so it should be y equals, and then you plug that 4 in where it's supposed to go. Yeah, so the c equals is not your final answer. The equation with the c plugged in, that's your final answer. Is that what you're asking?
Y be like number like.
So in these ones, y should be an equation. Like these particular solution ones, y should be an equation. I think you might be thinking of the last unit where you have an integral that has bounds. If you have an integral with bounds, your answer is a number. That's not going to happen in this unit at all. Just general antiderivatives. Anything else? Other questions? Yeah.
So when you sketch the particular portion of the slope field, it doesn't need to be like very exactly.
Yeah, so it's, I mean, as long as it's the right general shape. Like if it's supposed to be a parabola, but you drew something that looks like an exponential function, like that's not going to be right. But if I'm not going to get super, super picky about like, oh, the y-intercept was supposed to be 3 and yours looks more like 4. Like I won't get that detailed. But it's just, it's a very subjective thing, unfortunately. Like, that looks right, or like, nope, not right at all. Anything else?